How you doing? I'm Mr. Rose, and again, I am still in a jury room. So here we are looking at a second problem from the same AP Chapter 10 set. Here we had a little roller coaster. There was a little ball here that had mass m, little r. There was this big loop-the-loop with a big radius r, and they told me big r, this radius, was much, much bigger than this radius, essentially implying that we don't need to consider that ball so much when it's in the loop-the-loop. That comes in actually at the end of the problem. So they gave us a moment of inertia. They didn't give us of the little ball here, and they didn't give us a number. They gave us some equation. B is some constant, mr squared. And our first question was, what is the minimum speed that this ball needs to have in order to get just across or just over the loop? Now, this right away throws students for a loop because now you're thinking, oh my God, there's rotation. I got to start dealing with this. You're thinking way, way, way too hard. The minimum speed required is just an F equals ma. So if you got stuck on that, it's because of the way the problem is set up, and they gave this moment of inertia to you right away. We know F equals ma. We know when it's at spot A, there are two forces acting on it. There's the centripetal force, which happens to be the mg, and there's the normal force, which is also going perpendicular to the plane pointing down. The minimum speed to just traverse the loop has to be when that normal force goes to 0, which means the only force left I have here is mg. So when it's going faster, we know this normal force exists. When it is just there, and think about it, because if it's just too slow, it starts to come off the line. So we are getting when that minimum speed, the normal force, goes to 0. So it is just a straight application of understanding Newton's laws. We know F equals ma. In this case, ma is just F equals mg because that's the only force acting on it. And the centripetal force has to be that centripetal acceleration, which is mv squared over r. That is the centripetal force. Remember, they're not a new force. So we just compare them. We plug it in. mv squared over r equals m times g. Do some simple algebra. We get v equals the square root of g over r, which we have literally done 24 times. Part B now says that ball is rolling without slipping. That is telling you that there's some rotational energy. So we are, sorry, I don't remember what we were solving for. We are looking for the height of which it has to fall down. So in terms of variables. Is that true? Is that true? Yes, height in terms of variables. So basically, I want to know how big this is. So I set up my conservation of energy. Energy before equals energy after, which we know is potential plus kinetic equals potential plus kinetic. But when I have it at, there we go. When I have it at some spot at the top, we know that the kinetic energy is 0, so I just have mgh. Now, as it's rolling down, traversing through the loop, we know that, and you have to be a little bit careful here with your values. I tried to go step by step. We know that it's got some potential energy, which is just mg times r. That's actually where we need to be careful. That's not an r. You can see I corrected it down here. That's a 2r. Why is it 2r? Because when it's at its maximum height, it's a double radius, or the diameter apart. So this should be mg times 2r plus 1/2 I omega squared plus 1/2 mv squared, because there has to be some translational velocity, some translational kinetic energy. Rotational kinetic energy, translational kinetic energy, and now it's just a slew of algebra. And again, be careful because we have multiple r's. We've got this big R and we've got a little r floating around too. So I know right away, once I plug in for my moment of inertia I've got an m, I've got an m, I've got an m, I've got an m, m's go away, and I did this step by step. So this is the moment of inertia plugging in for the ball. Then the next step was, hey, what is my omega? Omega is v squared over r squared, and that has to be the omega of the ball. Make sure you have the right r there. So now I have my GH, potential energy, is G times 2R, twice the big loop-the-loop, 1/2 BR squared. This is a little r of the ball, 1/2 times G times R. We start canceling out terms. We should be left with height is 2R plus 1/2 B times big R plus 1/2 R. Combine all my terms. I probably could have simplified this more, but I felt I didn't need to. So I have 5/2 R plus 1/2 that constant B times another R. Now, I did not attach the picture here. Again, I was lazy, did not make a graph by hand. I just threw it into Excel. The picture is attached in our Google Classroom. But when I took the slope of the line on the computer, I got 0.199, which is about 0.2. If you were plus or minus that value, I'm sure you're fine. Part D said, hey, if we drop it from a height of 1.16 meters, we want to know what is that constant B. Now, this got really annoying to me personally because I said, hey, I've got this graph, I'm going to use the equation of the line. Now, my moment of inertia, I equals bmr squared. We're looking for this B. Equation of the line, 1/2 mx plus b, where this b is the y-intercept. X is actually the b that we're looking for in this case. They could have chosen any other letter. They didn't. That was obnoxious to me. So I have the equation of the line. I have my slope. So I say y is the equation of the line equals my slope, 0.2. X, remember that x is going to be their b, as we know, plus 0.9993. Again, if you did this by hand, I'm sure this 0.9993 would be something a little bit different, but that was just one. That was my y-intercept. Your y-intercept might have been 1, might have been 0. So this is by hand, 0.2 plus 0.2x plus 1. Imagine you did it by hand. And I picked the y value that they gave me of a height, 1.16, and I got a b, or an x in this case, the x value, to be 0.8. Last step was just calculating the value of r. Once I had everything there, I had my h, I can calculate r, and I had my b, I can calculate r. And the last part, this part is probably the hardest part to me, to be honest, because it's the application. Do I understand what's happening? So if r of the ball, all right, if this r of the ball was not negligible, in other words, maybe it had some significant size compared to the loop-to-loop, how does that affect the height of which you need to drop the ball? Now, what I did is I compared my thought process was comparing how fast that ball is going to go. So if r of the ball is bigger, then if I dropped it from that same height, 1.16, if I track the center of mass, it is going to actually fall a smaller distance. Thus, the loop is going to be smaller. Thus, my minimum velocity would be smaller. So if r was if r was not much smaller than big R, in other words, if r was not negligible, then the release height would have to be less. So if I started with v equals the square root of g times r, which we know, if r is not negligible, then the ball is not going to go as fast. If r is smaller, b is going to be smaller. Thus, it will require a smaller height. That's all I have for you. Our court officer came in for a second. Please feel free to like, click, or subscribe. And if you have any questions, shoot me an email. See y'all later.